Everything so far has lived on a line. One input goes in, one number comes out. But real problems depend on many things at once. So let the input be a point on a floor with 2 coordinates, and let the output be a height above that point. Now the graph is a landscape with hills and valleys. To draw a landscape on flat paper, we use contour lines, exactly like a topographic map. Each ring joins the points at the same height. Tight rings mean a steep slope, wide rings mean a gentle one. Here the rings close in on a summit. Toward the center is uphill, toward the outside is downhill.
So the whole shape of the hill is right there in the spacing of the rings.
It is. Now we ask the old question in this new world. Which way is uphill and how steep? The trick is to change one thing at a time. Stand at a point on the floor. First, walk only east and west, holding your north position fixed. The height rises or falls, and its rate is an ordinary one-dimensional slope. That is the partial derivative in the first direction, the slope of the surface, if only that coordinate is allowed to move. Now do the same the other way. Freeze the first coordinate and walk only north and south. That slope is the second partial derivative. So a surface does not have a single slope. It has one slope for each direction you could step. 2 inputs, 2 partial slopes. The natural next question is how to combine them into a single answer for the steepest way up. Take the 2 partial slopes and stack them into a single arrow, one component for each direction. That arrow is the gradient. And it is not just bookkeeping. The gradient points in the direction of steepest ascent, the single most uphill way to step from where you stand. Its length tells you how steep that climb is. There is a beautiful fact hiding here. The gradient always crosses the contour lines at a right angle. It makes sense. Along a contour, the height does not change at all, so the steepest way up must point squarely away from it, straight across the rings. Follow the gradient, and you are always taking the most direct path toward the summit. One more piece, quickly. The gradient tells you the slope, but not how the slope itself is changing. For that we look at curvature, how sharply the surface bends. On the map, curvature shows up as the spacing of the rings. Rings packed tight mean the ground bends sharply. Rings spread wide mean it bends gently. Gathered up across all the directions, that bending is called the Hessian, the second derivative in many dimensions. And now the payoff we have been building toward. Walk toward the summit and watch the gradient. As the ground levels off, the steepest uphill direction gets shorter and shorter. Right at the very top, there is no uphill left at all. The gradient is 0. That is the criterion for a peak or a valley. The high points and low points of any landscape are exactly the places where the gradient vanishes. Curvature then tells you which one you have found. So in many dimensions, the derivative grows into the gradient, a vector pointing straight uphill, and the second derivative becomes curvature, the bending of the land. This is not an exotic corner of the subject. It is the main road. In statistics, that uphill vector is called the score, and the curvature is called the information. In physics, forces are gradients of a landscape of energy. And in machine learning, this surface is exactly the terrain that training walks across. But knowing the top is where the gradient vanishes is not the same as reaching it. When you cannot just solve for that point, you have to walk there, step by step. That is optimization, and it is next.